Howdy, howdy. This is Mr. Potter. What we're doing in Chapter 6 is we're talking about how to find antiderivatives. In other words, how to find functions whose derivatives are a known quantity. In other words, how do we work backwards from taking the derivative? And it works really well if we have a function that's relatively simple. If it's exactly like one of the forms that we found antiderivatives for back in chapter 3. So if I see 1 over 1 plus x squared, I know I can do tan inverse to get that antiderivative. Or if I have 6x to the 5th, I know that I can use the power rule to get x to the 6th. And so I'm able to find functional solutions to differential equations, or families of solutions that all differ by a constant of integration C. But what we're going to be talking about today and tomorrow is how to take care of those situations when a more involved technique was done. So I want to start by taking a look at a quick derivative. I'm going to take the derivative of x cubed plus 4 to the 6th power. And so if I want to take the derivative of this function, because I have a composition of functions, we're going to have to use the chain rule. And so if I take the derivative of this, I'm going to end up with 6 times my expression x cubed plus 4 to the 5th times the derivative of what's inside the functions. So times 3x squared. And so I end up with 18x squared times x cubed plus 4 raised to the 5th power. So I can take this derivative fairly straightforward. The question is, if I had not seen any of this, and I just came across the problem to find the antiderivative of 18x squared times x cubed plus 4 to the 5th dx, I have no idea how to approach this problem, because this looks extremely complicated. And I could do binomial expansion and end up with 6 terms in this binomial expansion and integrate each of those terms, but that's too much work. So what we're going to talk about is how to undo the chain rule. Remember that this idea behind this is that if I want to deal with the integral of 18x squared times x cubed plus 4 to the 5th power dx, this is a hard indefinite integral. So I'm going to have to undo the chain rule. Now remember that the whole reason that we did the chain rule was because we were trying to take the derivative of a composition of functions. And so what I really need to do is identify this innermost function. So from the parts that I have here, I'm going to see one part that's still a composition of functions, and I'm going to see a second part that's just the g prime that's multiplied at the end. So I'm going to look for the composition of functions. And in this case, I see that I've got this x cubed plus 4 to the fifth. I see that I have a composition of functions. And so I have a clear f of x, which is x to the fifth, and I have a clear g of x, the x cubed plus 4. And what I want to do is I want to let u be that innermost function. In other words, what we would have called g. So if I let u be x cubed plus 4, then what I'm really dealing with is u to the fifth. And the idea of taking this complicated function within a function and being able to rewrite it as a simple power is going to be very, very powerful for us. So this is u. U is 3x, x cubed plus 4. So the derivative du dx is equal to 3x squared plus 0. And so what this means is if I want to be able to take an integral, if I want to take an antiderivative, I need something to indicate my independent variable is not x anymore, but instead is u. And so what I need is I need to know what the differential du is equal to. And my differential du is equal to 3x squared dx. So the first thing I had to do is I had to look for composition of functions. And the second thing I did is once I found a composition of functions, I wanted to let u be that innermost function. And I have to find du. And then what I'm going to have to do is rewrite remaining terms as a constant coefficient times du. So the thing is, I know that if I see 3x squared dx, that's going to be du. What I have instead is 18x squared dx. What I have instead is this part here, this part here. And so together they're going to form this 18x squared dx. The question is, how do I get from this step to this step? To get from this 3x squared to 18x squared, I have to multiply times the constant coefficient 6. And so what I end up with is I end up with u to the 5th times 6 du. And this is now my new indefinite integral. Notice that doing this substitution, being able to rewrite my integral as a function of u with a du term allows me to find something that's relatively easy to find the antiderivative of, especially if I rewrite it as 6 times u to the 5th du. Because I know from the power rule that the antiderivative of 6u to the 5th is u to the 6th plus a constant. So what I'm going to do is I'm going to find the antiderivative using our usual rules. And so this is going to be what that definite indefinite integral is equal to. The issue is that my function was not a function of u. My function is actually a function of x. So my last step here is to rewrite in terms of x. So I need to rewrite this as not u to the 6th, but what u is equal to. U is equal to x cubed plus 4. And so my indefinite integral of 18x squared times x cubed plus 4 to the 5th dx is equal to the quantity x cubed plus 4 to the 6th plus a constant. And so it's the series of steps that we're going to be dealing with here to find antiderivatives using what we call u substitution. We're really undoing the chain rule. So remember, the first thing that we did is we looked for a composition of functions. And we're going to want to let u be the innermost. And then once I've done that, I'm going to find du in terms of dx. I find this by taking the derivative and then multiplying both sides by the differential dx to get du, the differential by itself. And then once I've done that, I'm going to find the antiderivative by whatever rules we've already established. I can use the power rule. I can use one of our memorized antiderivatives. Any of those would work. But the last thing that I need to do is I need to make sure that I rewrite in terms of my original independent variable. And for our purposes in this lecture, our independent variable is just going to be x. This rule is challenging for a lot of people because we end up with very complicated functions that we have to find a way to work backwards on. And so practice really is the only way to get better at undoing this chain rule, finding antiderivatives using substitution. So here's my first of 4 examples. I've got 4 sine cubed x times cosine x dx. And if I'm looking for the most complicated part of this function, I'm looking at this 4 sine cubed x. And I definitely have a composition of functions. Something's being cubed. The something that's being cubed is sine x. And so I'm going to look here to find out what I want u to be. I'm going to let u be sine of x. And if I take the derivative of sine of x is cosine of x. And if I multiply both sides by the differential dx, I get an expression for du in terms of dx. Remember, I do this by taking the derivative and then moving the differential of my independent variable to the opposite side. My job is to make sure that I'm able to rewrite everything else in my function in terms of this du. So the thing is, du equals cosine of x. I've taken care of the sine of x cubed. What I've got is a 4 and a cosine of x and a dx. And I've got the cosine of the x times dx. I'm just missing the 4. So if cosine x dx is equal to 1 differential u, then 4 times the cosine of x dx would be equal to 4 differentials of u. So now if I actually rewrite this, this becomes the antiderivative of 4u cubed du. And so now I can just find my antiderivative using our traditional methods. This becomes u to the 4th plus a constant. So I've substituted, I've found the antiderivative, and now I need to do that last step. I need to rewrite this integral, rewrite this function as a function of x. Well, what is being raised to the 4th power? It's sine of x. So I've got sine of x raised to the 4th power plus c, or sine to the 4th of x plus c. Either one of these would be perfectly acceptable. Again, notice what the first thing I had to do. I had to look for my composition of functions. I had to identify u being the innermost of that composition. I had to find an expression for the differential du in terms of my differential dx. But not only finding du, I needed to find something that was equal to the remainder of what I had inside this integral symbol. So I had to come up with something that incorporated the 4 as well. And in that substitution, substituting this, and of course du is cosine x dx, and this 4 is just a constant, I can deal with that. That's not an issue. So that's my first of 4 examples. Here's our second one. I've got e to the 3x squared power times 6x dx. And as usual, I'm going to be looking towards the most complicated part. This appears to be the most complicated part of my indefinite integral, this e to the 3x squared. So if I look at e to the 3x squared, I notice that I have a composition of functions. I've got e to the u, where u equals 3x squared. So I've isolated u. It's from my composition of functions. It's the innermost function if I think of this as an exponential function. like this. That really is my innermost function, exponentiation. So if this is u, I need to identify what the differential du is. And I do that by taking the derivative, 6x, and multiplying by the differential of my independent variable dx. Now, this is du, which means I'm looking for this in my integrand. And if there's anything else that I've got, I need to incorporate this to try and resolve the du. And I'm lucky because all I have is just the 6x here. So this problem becomes the integral of e to the u du. And it's a very straightforward antiderivative. The antiderivative of e to the u would be e to the u plus a constant. But I need to go back and make sure that I write this as a function of my independent variable. My independent variable was not u, it was x. And so this becomes e to the 3x squared plus a constant. So when I'm looking at these, I really need to take a look at these in terms of, do I have a composition of functions? And I'm always going to look to the most complicated part of my function to figure out what u is. So in our third example, I've got a little bit different here. I've got 2x over 1 plus x squared. And a lot of people looking at this would say, well, I've got 1 plus x squared, but it's not really a composition of functions. I mean, they could see that if u is equal to 1 plus x squared, then du would be 2x. And we've got some good things going on here. But a lot of people will forget that this is really the antiderivative of 2x times 1 plus x squared to the negative 1. And so often, not all the time, but often, when I see a fraction, I'm going to let u be the denominator of that fraction and see where that takes me. Sometimes it'll help out, and sometimes it won't. And we'll be talking about that in just a few moments. In this case, though, what I've got here is I've got two different functions, and now it's real easy to see what my most complicated part is. It's this part here, including this exponent. So if my composition of functions is 1 plus x squared to the negative 1, I'm going to want to let u be 1 plus x squared. And if I do that, the differential du would be equal to 2x times the differential of x, which I'm lucky I have that. So what I've really got is the integral of 1 over u times du. Now, you may not see that if you leave this as the integral of u to the negative 1 du. You might be inclined to use power rule. But if I do that, I'm going to run into some problems. Adding 1 to the exponent and then dividing by my new exponent. Not good. But if I rewrite it back as a fraction, then I end up with 1 over u du, and I know that the antiderivative of that is the natural log of u plus a constant. Now again, I can't leave u in this function. I need to rewrite this as a function of x. So I got the natural log of the expression 1 plus x squared plus c. And I'm not going to have these absolute values here because the expression 1 plus x squared is always positive. So I could leave it as parentheses 1 plus x squared inside the natural log. That's perfectly acceptable. So, last example, let me make a slight tweak to this function. So I've got the integral of 2 over 1 plus 4x squared. And so what I'm going to be doing is looking at this from my first instinct. My first instinct, because Mr. Potter said that I'm going to want to let u be my denominator. 1 plus 4x squared. And if I let u be my denominator, then du is supposed to be the derivative of that. Du in this case would be 8x dx. And all I have is 2 dx, and so this becomes 1 over 4x du. And the problem is that I'm not able to completely eliminate my variable x in this way. No matter what happens, I'm either going to have an x over here with du, or I'm going to have an x over here with the dx. And I can't completely eliminate that variable. And so this is no good. And that's why I said usually we'll let the denominator be u. In this case, it doesn't, because I'm actually using a slightly different rule here. I know that if I was dealing with the integral of 1 over 1 plus u squared du, that would be tan inverse of u plus a constant. And that's actually what we're using here, because this has a variable squared in the denominator, but does not have that variable in the numerator that I'm missing. So since I'm missing that variable in the numerator, I really want to take a look at it from this standpoint. So in other words, u is going to need to be whatever this term is here. So that means that u squared is really going to be 4x squared. In order to make it fit the formula for tan inverse. And if that's true, then u is going to end up being 2x. I'm going to only look at the principal root here. I'm not going to look at the negative, but I'll show in just a few moments how it doesn't matter which one I use. So if u is equal to 2x, then the differential du is equal to negative is equal to 2 times the differential of x. And this happens to be exactly what I've got up here. So this becomes the integral of 1 over 1 plus u squared du, which is tan inverse of u plus a constant. And I need to make sure that I rewrite this as a variable of x. So this ends up being 2x plus a constant. Now, if I had instead, using this u squared equals 4x squared, looked at u to be the negative root 2x, then du would be negative 2 du. And I don't have a negative 2 here. What I've got here is a 2 du. And so this actually gives me negative du. And so this becomes the integral of 1 over 1 plus u squared times negative du. And this negative is really negative 1 times du. We don't often write that 1, but whenever I do for substitution, it often helps. So I end up with the negative tan inverse of u plus a constant, or the negative tan inverse of negative 2x plus a constant. But because tangent is an odd function, tan inverse also ends up being odd. And the function of a negative variable eliminates this negative on the outside, so I end up with tan inverse of 2x plus c. I end up with the same thing, no matter which of these roots, the principal root or the negative, I start with. So this is just a start with dealing with integration by substitution. We're going to continue this in tomorrow's lesson, but I wanted y'all to get into the habit of this. Being able to look at an expression and identify what u is going to be using the composition of functions that we talked about when we discussed the chain rule. Find the differential du and substitute to make your integrand a much easier expression to take the antiderivative of. Just do not forget this last step, replacing u as a function of x. This is Mr. Potter. Thank you for watching. Have a great day.